Okay, so we're talking about the conduction model. Now, we've already worked out and the transition problems really, I think, give you pretty good introduction to the conduction model. And then we did some labs back when you were assigned that originally. So I think people should have a pretty good idea of conduction model, but the essence is I'm going to present it is electric field is a negative potential. Now, if your potential is going up, that means you're going toward positive, right? And if you're going toward positive, then a positive charge is going to be pushed this way, opposite to the potential. Okay, so you're actually, your electric field is a negative of your potential. So you want to understand that. Your text will explain it. And we've already seen it. Okay. You add that to, you put that together with the conductivity and you get the current density. Okay. And current density is generally represented by the symbol J, which is current per unit area and perpendicular to an area. Okay. I didn't mention the perpendicular, but that should be critical. So it's equal to conductivity times a negative of your potential gradient. The potential gradient is going to have a direction in space, because, well, at this point, you know what a gradient is in three-dimensional space. And your textbook gives you the expression I put on the board previously. It's just a gradient of your potentials, capital V, since partial with respect to X times I, partial with respect to Y times J, partial with respect to Z times K, operating on the V vector, and you know what that looks like. Okay. And it's there in chapter summaries, and we've already covered that chapter. Okay. So now I'm going to say this conductivity thing is the concept that I usually like to start with, because it's positively related to your potential gradient, just what you multiply by your potential. More commonly, you can look up a table of conductivities and you can look up a table of resistivities. You take the same material, conductivity will be the reciprocal of the resistivity, because conductivity, the greater your conductivity, the greater your current is going to be. The greater your resistance, the less current is going to be. They have a reciprocal relationship, pretty easy to understand. So you want to make sure you understand that. If you put that together with this, what do you get? Well, your potential gradient is negative. Your potential gradient is E, the electric field, and your conductivity is reciprocal resistivity. If rho stands for resistivity, which it pretty universally does, then you got 1 over rho times E. And that could be rearranged to rho equals E over J. But I think it's easy to understand this. I think it's easy to understand if there's this conductivity that you multiply by the electric field for given material to get the amount of current per unit of cross-sectional area. Okay. So this is a little bit obscure. And if you understand this better and you understand this, okay, these say the same thing, except you don't have arrows. I like the arrows. I like to express these as vectors. So that's pretty much it. You got drift velocity. Well, first of all, current. Current density multiplied by cross-sectional area. but it's cross-sectional area perpendicular to the direction of the current. Okay. So I'm not writing out all the words here. So we write that as I equals A times A. Or in general, the integral over the cross-sectional region of J dot dA. So the current through any surface R is equal to this M. Okay. If it's a closed surface, then you have net zero current. Because if it's a closed surface, you got current into it and current out of it. Unless there's a current source inside, you're going to get that. Now that's going a little further than what we need to really say. But if you understand that much, you're well on your way to understanding the conduction law. Okay. So again, I'm just trying to reconcile this with the presentation you'll have in your text.
Recording in
Okay, your text now gets a little more formal than we have. I've said, what we've dealt with in lab is a wire's constant cross-sectional area, potential difference across that wire, the current, conductivity, resistance, and so forth. Okay. We stated specifically, if you have a cylindrical wire, it's homogeneous. And homogeneous just means same material, same conductivity throughout, same resistivity, conductivity, resistivity, just reciprocal things. Okay. With the uniform cross-sectional area, potential difference B. Now B has a sign, maybe you're going from high voltage to low or from low voltage to high. I don't specify the sign here, but you go by the gradient. Okay. The direction of maximum increase, the electric field's opposite to that. Sectional area A, length L, potential difference B. All that implies E magnitude of E equals V over L, something you're very familiar with at this point. What's the electric field? Okay, it's newtons per coulomb, right? MV is joules per coulomb. You divide joules per coulomb by length. The joule has units of kilogram meter squared per second squared, which is energy. You divide that by length, one of those meters squared becomes a meter, and then you have the dimension of electric field. Okay. So joule per coulomb divided by length gives you units of newtons per coulomb. And you should be used to that, because that appeared many times and reinforced in many ways in the transition problems. Okay, so that should be no surprise, but let's make sure we get it formally. Then again, for homogeneous wire, etc., E equals V over L. So J equals E over rho. Is V over, V over L over rho, V over rho L. So the current is times a cross-sectional area. I'll use ACS. And I'll put a CS in this A. Smudge, you can't read it. but- ACS, like Phil. Okay, so when you multiply your current density by your cross-sectional area, you get V times A CS. Go times up. Okay. And it makes sense. Greater your potential difference, more current you're going to have. More cross-sectional area, the more current you're going to have. Greater the L, the less your electric field is going to be, and the less acceleration your electrons are going to experience, the less their drift velocity. Okay? Does that make sense? That connect? And if you're well prepared with this stuff, it should maybe bring what you learned in the transition problems into nice contact summary. Okay, and that's what we're really trying to do here. All right. Now you do have things like drift velocity, which is related to the number of charges and stuff. I'm not even going to talk about that today because I think that was done pretty well in the introductory problem sets and the transition problems. You just take how many charge carriers there are per unit length. Okay. And then you figure out how long it's going to take those to move that length. Divide number of charges by that length. And you get the curve. Okay. And that's the fundamental idea, although something you got to think about a little bit, but I think you have. Okay, so if not, read it. It should come back to you. Okay. Now there's a little bit more about resistivity. Yeah, a couple of things. One thing that's kind of important in engineering applications is resistance isn't constant. It varies with temperature. Okay. So resistivity, this is something new, because the condition problems, I don't think talk about the temperature coefficient of resistivity. Okay. Now let me make sure I've got the symbols right, but it's just resistivity equals the resistance usually at some reference temperature, which is often room temperature or maybe 0 Celsius. Yeah, the find my picture. If I don't show the camera, I could do this. I still kind of like this, although it turns out it didn't work out. It was a miracle that occurred back in. What was it? Late September, early October. Okay. It was a pretty neat miracle, and figuring it out took a while. Okay. That model didn't work. Turned out there's some kind of subtle going on that took me a while to grasp and making an assumption that something was negligible when it wasn't. It's pretty neat. So again, I wanted to talk about the temperature coefficient of resistivity. So you take your resistance at some basic temperature, and then you've got a temperature coefficient of resistivity, and you multiply that resistivity by 1 plus that coefficient times your temperature difference. Okay, I just want to look at the symbols that are used. What? Okay. Okay, so what this says is you have some 0 point resistivity. Okay, so rho naught is your resistivity when the temperature is T naught. Because clearly if the temperature equals T naught, this is 0, and you just have rho naught times 1, right? Well, that's not why this is it. This is the resistivity that you measure at some known temperature. Usually 20 Celsius or 0 Celsius, okay? And I'm just doing that off the top of my head. If you look at table, looking for the word, if you look at a table of resistivities, any decent table will tell you what T naught is. And then it'll tell you what rho naught is, and it'll tell you what alpha is. This is an expression okay, well, here is a graph of rho versus T. Okay. You have a T naught, then you have a rho naught. So right there is a point on the graph of rho versus T for whatever the material is. Now, generally, this thing is going to be some sort of a curve. It depends on the material properties. Your resistance is going to be pretty much linear over some restricted domain. I call this the domain of approximate linearity. You can see that this curve actually has a little bit of a downward concavity at this point. It's like an upward concavity. It depends on the material. It comes down to the quantum mechanics, and I can't derive it from the quantum mechanics. Few people can, other experts in the subject, which is no excuse. I ought to be able to derive it, but not. Okay. So what we're going to say is, in this domain, approximation I like to use delta T instead of T minus T naught. But your book uses T minus T naught. Yeah, I'm just trying to avoid confusion by using the same notation, although I think maybe I like the idea of thinking of a delta T here. It's closer to the way it's done. It's mathematical. Well, never mind. It's a differential. Okay, this is a differential of this function here at this point, or somewhere in the vicinity of this. So even make a note. Is that a differential? Not exactly, because the differential would be based on the slope at this point. On your domain of definition, it might be based on the endpoints and some adjustment, some best fit, et cetera. Okay? Depending on how whatever expert, who won't be me, but to uh, uh, determines for all kinds of reasons, a lot of which I would not be aware of, okay, unless I looked at the research and understood what I was looking at, you know, a lot of jargon there. One way or another, you can understand this. What I want you to understand here is that what works over a certain temperature range, and a good table is going to tell you the temperature range, and it's going to tell you the degree of accuracy of that linear approximation. Okay. And that might or might not be important. Trying to get a very precise result. You want something even more precise than this linear approximation. You might want a quadratic fit to this thing or some other kind of fit. Okay. All right, well, anyhow. So you could have a 1 plus alpha t minus t naught plus a beta times t minus t naught squared. And maybe a gamma times t minus t naught cubed. You do like think of Taylor series. Okay, it's like a Taylor series approximation. This is the first term of the Taylor series approximation, or whatever this thing is from this interval. Okay. And kicker is that rho as a function of temperature T is not some nice closed form function. Okay. I would say pretty much never for real materials, but you can approximate it very, very closely by taking really good measurements. All right. So that's more information than you probably want to digest, but it's, I think, worth digesting. Something that I wish somebody had explained to me when I was taking this course. If I could use that as fun, but what's the real mathematical perspective? Of course, when I was taking this course, it was as a freshman when I was just learning calculus, so I wouldn't have understood. Okay. So I think it's nice that in this engineering curriculum, getting it after adding your calculus. So you can kind of understand what I'm talking about. Okay, this is temperature coefficient of resistivity. At least that's what I call it, whatever your book calls it. Call it that. But I'm pretty sure that's a pretty standard term. Okay. Okay, now a brief look at terminology in the chapter summary, which is what I'm trying to bring this into, okay? It's pretty consistent with the terminology we used to. You go like this. Bulk of a given material, it's going to have a resistance. So much that I didn't pay any attention to where my parentheses was are. Not apply by. Okay. This is saying almost exactly the same thing this is, except this uses delta T like I wanted to over here. Okay. Now, why it's written this way here and this way here, I have no idea. I don't really care because you should understand it both ways. And whatever way somebody chooses to write it, it's okay. If I want to use delta T over here, it's perfectly valid. It's probably what I did in the transition problems. Okay, I didn't look at them that closely. I wrote them, 100 years ago. I mean, over 30. Okay, it's about 100. It's a geometric mean type thing. It's kind of halfway to 100. And then delta T here, if you want to use T minus T naught instead of delta T, have at it, whichever makes more sense to you. I think the delta T makes more sense in terms of the idea of a differential. And you want to connect that with what you're seeing in multivariable calculus or what you saw in multivariable calculus. Some people had the multivariable calculus last year ago. Okay. So that's not a difficult concept, and I think the problems that you involve it, as long as you understand the concept pretty well, should be pretty straightforward. Okay, let's go back to what I was saying just a little while ago about I equal current density times cross-sectional area. Current density is E over J. Is 1 over rho times E. E is V over L and all that stuff. Okay, comes down to this. Well, what I was leading up to was Ohm's law, but I never said it. I equals V over R. Equals times L over cross-sectional area. Now that's pretty easy to make plausible. And here's a rigorous development of it. You should understand that completely in order to apply it to some of the problems that I haven't yet selected, but will separately. Okay. So resistance is rho times L over cross-sectional area. What's that mean? It's proportional to the resistivity. Greater resistivity means lesser conductivity, which means greater resistance, right? Greater length means your voltage is spread out over a greater distance, which means your potential gradient is less, which means your electric field is less, which means you're accelerating the electrons less rapidly. Okay. In that electron cloud thing where you got these, big old mess of colliding particles. They're moving like that out of a hot place. Okay, and much faster, actually, well over the speed of sound. But you can't hear them because they're subatomic. Well, anyhow. Okay. They're bouncing around like crazy, just like a cloud in the sky. We got particles doing all kinds of things within the cloud. Cloud is drifting off some more or less constant velocity. Okay. So again, the greater L, the less electric field and the less velocity you impose on this drifting cloud. And then the greater your cross-sectional area, the more current you're going to have because the current density multiplied by cross-sectional gives you the current. Okay. The resistivity and the length of the wire determine the drift velocity, therefore the current density. And then cross-sectional area tells you what the current is. The resistance will be less if you have a bigger cross-sectional area because you got more charges drifting at the same velocity as you would have for the same potential gradient with a smaller wire. Okay. And to put all that together, understand that. Okay. And this is expressed in this form, or even not usually in the form R equals V over I. This is the usual form. This is just generally regarded as a rearrangement. It's very sloppily written, so rewrite it. No, I've made this sloppy. You can understand it intuitively in all three forms. I like this form because it's closer to the derivation. This form maybe is easier to remember if you're based on, if you're working for memorization. You really ought to understand its development. If you do, it's going to be easier to think through the problems. It's going to be easier to understand what happens in a circle and so forth. You don't always want to break it down to all that people, but you want to be aware of it. Okay. That's pretty much the chapter, but I want to look at some of the problems, which I would have done, except I was busy looking at the chapter. Comes after this, that we'll do next time. Okay. Because I don't know. Okay, the chapter does address superconductivity. And I don't know a lot about superconductivity. Okay, I read Layman's description and try to read a little bit into it with the a little bit of superconductivity related physics that I understand. But interestingly, reminds me of one of the neatest experiences I ever had. That you get a few times in a lifetime. The Michelson-Morley experiment, one of the most famous experiments in physics, was done on the campus of my university. Okay. Now they think somebody else owns it, but I think I do. Seriously, it was done. I think I could have thrown a football. I had a pretty strong arm, not anything to brag about, but pretty strong. I think I could have thrown a football from my graduate school office to the point at which the experiment was done. You know, a quarter of a mile away or something like that. No, it was done well within 100 yards. Okay. And I think at that point, I could throw a football down 55. I might have made it, might not, something around that range. Okay. And I wasn't a candidate for quarterback because I couldn't hit the broadside of a barn, but I took beautiful things. Nobody knew where I was going to land. It was a jump ball every time. So anyhow, everybody was invited to this Michelson-Morley centennial. Okay. It was a big centennial held right there on campus, right there at Severance Hall, where I engaged in many friendly brawls, fraternity stuff, with pledge classes and stuff. Where people were trying to throw people into the lagoon, other people trying to prevent it. I lived for those things. And right across the lagoon is the Cleveland Institute of Art, Major Art Museum. Okay. So at this centennial, Hans Bethe described how he figured out what goes on inside of stars. Okay. Maybe the most eminent physicist alive at the time. Uh, and Sheldon, I think, there were like 8 Nobel laureates there. Okay. And they all wanted my advice. No. Okay. And um, one of the presentations, this was when superconductivity was high temperature superconductivity, above the temperature of liquid helium. Superconductivity could be achieved at the temperature of liquid nitrogen. Or maybe it was liquid helium, liquid hydrogen. Anyhow, a few degrees above absolute zero, and then moving on toward temperature of liquid nitrogen. Brand new, really exciting. One of the best presentations I ever saw by one of the discoverers. He just came up there and boom, 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 boom. And he kind of had slides because, we didn't have computers with projectors at that time. He's showing slides and boom, boom, boom. What a great presentation I've ever seen. It's very neat to see. And then this thing adjourned. There was this composition, Let There Be Light or something like that, by Philip Glass. Commission that was performed by the Cleveland Orchestra. And then we went to the art museum, which was closed down, and they opened it to us. And they served these really good fillets. They had an open bar. So I asked for, just a little shot of bourbon or something like that. I got half a glass and I felt obligated to drink it. Okay. That's quite a bit of bourbon. I wasn't staggering or anything, but I was in a different state of mind. And I usually don't, but I was wandering around the art museum, and there's this famous Don Quixote sculpture out of iron. Okay, just ironwork. And I look up and see, okay, who did that? And I saw my name. In that state of mind, surrounded by Monet water lilies and other stuff, it was very interesting. So that's kind of what I know about superconductivity, but if you're really interested in it, I'll pull it up on it a little bit and read what's happened in the last 40 years and show you a little bit more about it. I could tell you a little bit off the top of my head, but it wouldn't be as enlightening as is what you think that if I pulled up on it a little bit. Okay, well, that's a big digression, but in the field of physics, interesting things can happen. Okay. So there's this problem. Now, I had a little trouble with this thing because I didn't look at the labels of the axes because they're really small print and I don't have my glasses on. But this is going to be the Z direction. And then we're going to have X and Y here. Okay. And then you have a big block of material. So I'm going to put the block of material, I'm going to have it sitting on top of the XY plane. Okay. Dunting block. It has got dimensions. Maybe it's A by B by C, but I'm going to have to look. And you have a constant, I think a constant electric field. Or maybe it's constant current density. That's what I'm gonna have to look at. Okay, actually, I think you're given the current density. Okay. I think you're given J equals like an A, E to the KX. Times your K vector, and you want to know what the current is through one of these faces, through one of the vertical faces. Well, through one of the faces that's perpendicular to the K vector. Okay. Now let me get the numbers. I remember. Okay. Now, let me modify this. I have the thing, right? I think it might have been e to the alpha x instead of kx. And of course, that's badly written J. Let's put it into space there. That we call this e to the alpha x instead of kx. It's the same thing. Where and this isn't a vector, but the k makes it into a vector. J naught is 0.35. It's in amps per square meter because the density is in current per unit of area. Okay. Then what I don't know is alpha, but I'll look back and see what that is. I can't keep that much information in my head reliably. We want to get it accurate. Chapter 8. Alpha has magnitude 2.1 times 10 to the negative third. You're going to multiply it by x to get a unitless number because you can't do e to a number with units, okay? Alpha x has to be unitless. X is in meters, so alpha it better be in reciprocal meters. Now the question is, what's the current through this space here? Now your book has a better picture. And it confused me when I first looked at the problem because I'm used to the z-axis doing this, but okay. And again, I didn't read the letters and I was asking myself, how in the world is a field or a current density in this direction give you a current through this face? The current density in this direction will give you a current through the top or the bottom, both. And it's just that I wasn't seeing. I finally took a close look, saw that there was a cave there. So actually, your book has a k vector here, an I vector here, and a j vector here. Using that explanation. Because you're doing multivariable calculus and you're a little more used to mathematician, but it's really easy. Make those connections. Okay. So how do we figure current through this face? Oh, there are some dimensions. I'll give you the dimensions of the block, but think about how you would find the current through the face. Just give a little. I knew Zara had really little time to find it, but this is 3 centimeters by 3 centimeters. And this dimension doesn't make any difference. The dimension in the z direction because your current density is in the z direction. Okay. So Here's your X direction. How are you gonna start this? Give me a few thoughts if you can. If not, I'll supply 'em. Well, what could say, well, you were wanting to say, so this suggests the Herbert Wendy variant. And multiply by J. Well, that's great. What J are you going to multiply? Because J has an infinite number of variables. Okay. Well, then I suggested, well, yes, okay. Multiply by the average value of J. Okay. So how do you get the average value of J? Well, best answer I got to this point was, well, you add them multiply by how many there are. Well, there are an infinite number of them. So you're going to divide an infinite sum by an infinite number, right? So where are you there? Well, that's not bad progress, but there's a thing that I've been trying to get people to understand since, well, since late August probably. Okay, how do you get the average value of a function? I don't know what to do about this. This is a really important concept and it could cut through a lot of stuff here. Could be the integral of J with respect to X divided by length. That's how you do an average value. I mean, it goes back, look up the definition, which is one of the Pfizer list 10 things that you should absolutely know intuitively in the depths of your soul when you finish Calculus 1 and Calculus 2. It's a concept of average value. And I think the recent assignment I gave multivariable calculus asked a lot of average values. Okay. So you really need to have that concept. It needs to be something. Doesn't, yeah, it's pretty much necessary. It's very convenient for this problem. Okay, I think I am going to sign this problem. Actually, I know you'll be able to get the answer because it's very easy if you do use the idea of average value. I think your book asks you to set it up a little differently, and I'm going to recommend that you do that. Okay. But since the magnitude of J depends only on X, I'm not sure if this thing really goes from negative L over 2 to L over 2. I kind of think it does. The picture here I thought it looked pretty symmetric about the z-axis of that's what it is. That's the average value. And you should go back to Riemann sums and understand that that's every Riemann sum is a sum of values divided by how many there are. And when you take that to the limit, this is what you get. And you really need to understand how that goes to the limit. And since you said, right, you add them up and all that stuff, you're that close. Push it the rest of the way. Okay, well, that integral. Do that integral real quick. Give you a minute. You might be a little rusty, so you might not be able to get it in a minute, but see if you can. Most times, so just got enough, even the alpha x dx. Indefinite interval is just this by the chain rule, because what do you get when you take a derivative? Well, any derivative or integral of e to the alpha x will be a multiple of e to the alpha x. And am I recording? Yeah, I am. Okay, yeah. So, you know that, don't know how to, if it's not real clear to you how to integrate exponential functions, make sure it is, because you're gonna have to integrate them in molecular calculus and in physics, okay? So you have this. So, you know, what you get here, it's pretty straightforward, then you're gonna get. Well, let's say make up. The J naught over alpha. And make that J naught over alpha L. E to the alpha x between L over 2 and negative L over 2. We can be J naught over alpha L times E to the alpha L over 2 minus E to the negative alpha L 2. And then, of course, alpha has a meaning is 2.1 times 10 to the negative third per meter. So it's L. Okay. L is 0.03 meters, etc. So you just got numbers you can substitute for these things and then think about what they might mean. And you end up getting the current. I think it's going to be a pretty small current. I mean, you only got 0.35 amp per meter squared for J naught. And what you got is 9/10 thousandths of a square meter. About a thousandth of a square meter ballpark. And then alpha L over 2. Alpha is on the order of 10 to the negative third per meter. L is on the order of 10 to the negative second meter. It'll be pretty small. That's okay. You can still get it. And you're talking about currents still that are easy to detect with a lot of accuracy. Using, you know, microammeters or nanoammeters or picoammeters. You can make them pretty accurate.